Hi guys, it's Mr. Blake. Today we're going to be talking about chemical reactions again. We've already done one sort of introductory video, and today we want to talk a little bit about some of the more intricate details involving that. What is a chemical reaction, and what does it mean when we see these sort of figures and numbers pop up in one? So before we get going in the actual lecture, I wanted to do a little review from the previous lecture. So if you could, and this is going to take a little discipline on your part, but if you could take out a sheet of paper, and we're going to do an IQ. And this might require you guys to grab your ion sheets, but this is, as we mentioned during the nomenclature unit, a really important skill that you guys develop, because not every time will you see a chemical reaction written in the format of using the chemical formulas to indicate what's going on in that reaction. Sometimes they're going to be the words, and we need to be able to translate from the word form to the chemical formula form. So again, go grab, if you need to hit pause, go ahead and hit pause, but go ahead and grab maybe from up front one of the ion sheets. You can of course use your phone, you can use any resource available to you. You're on the internet right now, so world's your oyster. But if you could, we're going to start it up here on IQ number, and I believe it's number 4, it might be number 5, but whatever it is, go ahead and adjust it so that it works to what you have so far. We have 2 reactions, and you can see that they're both in word format. Hydrogen plus oxygen makes water, and then copper plus tin makes sulfite. Now the first one, and this is something I don't believe that we've actually talked about, but it's going to play a huge deal later on, especially when it comes to what we talk about today, and that is the idea of what a diatomic molecule is, or a diatomic element. There are certain elements that we only find in nature in pairs. And because of that, they actually make molecules. We mentioned it briefly with the hydrogen ion, but these aren't ions. These are just elements that are always found in pairs. And if you kind of think back to even maybe some of your time in biology, this might make sense. Hydrogen and oxygen are 2 of those. So if we look at both hydrogen and oxygen, they will never exist in a chemical reaction as H or O. They are always H2 or O2, because when we find them in nature, we always find them in pairs. And we call it, again, diatomic. Di meaning 2, atomic meaning atom. So just be aware of that. And this is, of course, really important when we get to the later topic today, which is balancing chemical equations. So let's look first at hydrogen and oxygen makes water. And right now, all I want you to do is understand that hydrogen and oxygen are both diatomic. Water is exactly what you know. It's dihydrogen monoxide, if we were to write it properly. But go ahead and write that one out. And then the one below, copper plus tin 4 sulfite yields copper 1 sulfite plus tin. Okay, so go ahead and hit pause right now if you need to, and then we will come back and go through them. Okay, hopefully you actually hit pause and you're not just waiting for the awkward 5 seconds where I stared at the webcam. But if you do that, hydrogen plus oxygen, and this is a really great time to talk about some of those diatomic elements. So this is what you should have got. H2 plus O2 yields H2O. And again, if you look at hydrogen and oxygen, always in pairs. Always, always, always. Even though we just say hydrogen or we just say oxygen, we're always going to find them in pairs. Now let's go ahead and look at the next one, which is a bit more complicated, you can see, because you're going to be required to understand some different charges that happen with some metals. Copper and tin, particularly, both of them can have multiple charges. If you recall, or if you don't even need to recall, you can just look it up. But copper can either have a 1+ or a 2+, whereas tin can be a 2 or a 4, depending on what it's being combined with. Now, sulfite is one of those ions that is not on your list that you needed to memorize. So it's SO3 2-, and the number of them that we have is really going to depend on what we're combining it with. So when we write copper, we're not actually writing it in the ion form. I was going to say ionic, ion form. I'm not going to edit this because I don't have time, but we're not going to write in the ion form. It's going to be just copper. Okay, so if we wanted to indicate copper 1 or copper 2, the equation itself would literally say just that, copper 1 or copper 2. It would not in any way just say copper and expect you to somehow magically know which copper it's referring to. Moreover, if it doesn't give you any sort of indication that it is charged, we can assume that this is neutral copper and we don't need to write anything special. Now the tin, however, because it's in a compound and because it's a metal combined with a non-metal or a polyatomic anion, we know that tin's an ion. And the fact that they give us the 4 right there should be sort of a big tip-off. Copper on the product side is copper 1, same thing, right? It's also written as with that Roman numeral inside of the parentheses. And then tin, when it's on the product side, it says copper 1 sulfite plus tin, right? So if we look at that, okay, if we're just going to look at tin, okay, or this guy right here, it doesn't give any sort of, it doesn't say tin, and I apologize for the penmanship, tin 4, okay, ooh, hey-o, or it doesn't say tin 2, okay, it doesn't give us any of that information, right? So if we go back, okay, if I can figure out how the heck to get out of here, there we go. Because it doesn't say that, we can again assume that it is going to be just one of those situations where it's not in an ion form. Okay, so it's usually going to be very, very clear about which is, if it's an ion or if it's not an ion. If it's an ion, it always has to say it. All right, and that's kind of the key point here. Okay, so let's look at the answer here. Okay, and if we bring it up, okay, we have copper plus tin 4 sulfite. Again, so sulfite is a 2- charge, and that is why we have 2 of the sulfites to match the 4 positive charges that come from tin 4. On the product side, on the right side of the arrow, copper is a 1+, as indicated by the Roman numeral, and sulfite, if you look it up on your sheet, has 2 negative charges. We have 1 sulfite, so again, how many copper 1s will it take to add up to the 2 charges? It will take 2 copper 1s, and that's why you see the Cu with the 2 in the subscript. All right, so without further ado, let's get going and get into this topic. Today we want to talk about equations as it pertains to the conservation of mass. And if you look in the classroom, right when you walk in on the left-hand side, there's a picture, and I know we've talked about him before. He's one of my favorite scientists, and he's a nice historical figure. His name's Antoine Lavoisier, and his wife, Madame Lavoisier. They were both beheaded in the French Revolution. Kind of a sad story. For those of you guys studying AP Euro, he was one of the guys that Talleyrand Robespierre in the Reign of Terror beheaded. So his father-in-law, unfortunately, be careful who you marry, was a tax collector, and that was none too popular in the late 1700s in Paris. So he got beheaded despite all of his incredible contributions, specifically to chemistry. He's sort of a legend in chemical circles. He had a few bogus ideas that we'll talk about later in thermochemistry, but he had some amazing ideas when it comes to this idea that in a chemical reaction, we're not making new things, even though it appears sometimes with a color change with smoke that something is coming of nothing. He said, no, we're not really doing that. What we're doing is rearranging the atoms and the molecules that are already there. We're breaking bonds and then reforming them. And that's what, when you see a chemical reaction written on paper, that's what we're describing. So in order to reflect that, idea that nothing new is being made. That in fact, we're just simply rearranging what we already have. We have to do what's called balance our chemical equations. Okay, and it's a very simple mathematic process. It really comes down to just simply adding and a little bit of guess and check. So I think you'll see once we get into this just how easy it can be. His law, the law of conservation of mass, or the law of conservation of matter, in chemistry specifically refers to atoms. Okay, because ultimately the simplest form of matter that we know of with an identity is just that, it's an atom. And it says when you're undergoing some sort of chemical change, which is a chemical reaction, there has to be the same number and type of each atom on either side of that equation, which is divided by, if you remember from the lecture previously, it's divided by an arrow. Okay, that separates our reactants, which is what we start with, from our products, which is what we end with. All right. So coefficients, okay, are the way that we do that. Coefficients are not part of any of the chemical formulas. So when you were doing chemical nomenclature, none of what you did, with one exception, that was the hydrates, had anything to do with coefficients. Coefficients are whole numbers, and they don't come with, they're not within the formula. They're not subscripts. They don't come after the parentheses. They're not little or big. They're whole numbers that precede, so they come before any of the species in a chemical reaction. And by species, I mean any atom, any compound, formula unit, any molecule. They're whole numbers that are written before, not within the compound nomenclature itself. And what they do is they indicate how many atoms or molecules. And essentially, you know, when we look at a chemical equation, it's very easy to look at it and go, oh yeah, it's one atom of this or one molecule of that. And we often, as chemistry teachers, we say this. We say a molecule of this plus an atom of that. But of course, you guys can imagine, you know, in a lab, do you think we're really reacting one atom or one molecule? Of course not. We're reacting, you know, trillions. We're reacting in the unit, of course, it's going to come back to, for those of you guys thinking ahead, are moles. How many moles are reacting? Because you typically, in any sort of, even in a really small scale setting, we're dealing with incredibly large quantities. Even we're doing drops of reactants making you know, millimeters or milliliters of product. We're still dealing with a pretty substantial number of atoms. So those coefficients typically represent the ratio of really of anything, but specifically the unit we look for is moles. And that's how you're going to see it phrased pretty much from here on out. All right, so let's show you what we're talking about. And the way that I'm going to teach you, there's actually a few methods, and we've taught a few different ways, but I like this method. It's called the tally method, and this is sort of a bit more simplistic, and it can be done in your head. For some of you, you're going to really figure this out quite easily. For others, it may take a little bit more practice. All right, so here we go. We're going to start with a chemical equation. And you can see we have a pretty basic one here. We'll have a unit later where we get into what are the different types of chemical reactions. But for this one, this is called a combination reaction. You don't need to know that name just yet. You will eventually. But right now, all we're concerned with is matter, according to what Lavoisier taught us, being conserved. That is, when this change happens, are we accounting for all of the atoms? Okay. So whatever's on the left side essentially has to be the same that we find on the right. And if you look at it now, okay, and we're just going to kind of, and this is why we call it the tally method, what we're going to do is we're going to take each part. So on the reactant side, we have aluminum and we have sulfur. Okay, and neither of those two are examples of the polyatomic ions that we saw with hydrogen and oxygen in our IQ today. But if you look at it, okay, we have two simple atoms, and then on the product side we have aluminum sulfide. And so on the left we can see aluminum. We have one of them, okay, as it's written currently, right? On the right, if you look on the right, how many aluminum atoms do you see in that formula for aluminum sulfide? Well, if you look at the subscript, there currently are two. Okay, for sulfur, there's one, and on the right side, how many do you see? Well, there's three. So what we'll do is we'll go down the left, and you can see I've done it here. we're going to write in the number of, and we're just going to treat it like atoms. Technically, I want you to later think of this as mole ratios, but right now, they're just atoms. How many we have of each. And you can see the most important thing is that they're not equal. They have to be equal. So even though this is how we write it, it's not exactly accurately represented as how we would find this in nature. Okay, this is not how this reaction would occur. You can imagine if we could react on a really, really small scale. You couldn't take a single atom of aluminum and a single atom of sulfur and create something with 2 atoms of aluminum and 3 atoms of sulfur. It's impossible. You can't create that from nothing. Okay, so what we have to do then is account for how would we get this? Okay, how do we get this? How many atoms of each would we need? And again, later I want you to start thinking is how many moles of each would we need? But for now, atoms and molecules work. So what I'm going to do, you can see the spaces there that are already allotted for you, is that I'm simply going to add in whatever I need to make them the same, to make them balanced. So on the left side, where I'm short, I'm simply going to put a 2 in that spot. And that is a coefficient. It's a big whole number that comes before our species. And the species here is aluminum. So now on my sheet, what I'm going to do is I'm going to change that. And I can see that it's balanced. So far so good. Now I'm going to move on to sulfur. Okay? And on the right, you saw I had 3 moles of sulfur, and on the left, I only had 1. So what I can do is in that coefficient spot, I'll put a 3, and there you go. And I can go back and make sure that I haven't changed anything, and this one's good to go. So the numbers on each side are balanced. I am completely happy now. To be honest, this is a really, really simple one, and it's a good starter. But as long as you understand the idea that they have to be the same number of atoms on either side. Okay? All right, let's try the next one then. So here, I got something a little different. I have lithium and oxygen making lithium oxide. This is another what we call combination reaction. All right, so let's do the same thing we did in the last one. What I want to do is count the number of atoms of each element represented. All right, so on the left I see lithium and I see oxygen. Okay. Now, how many of each do I have? So on the left, how many lithiums do you see on the left side of the arrow? If you can look in both species, and there's only 1. Right? But on the right side, in that lithium oxide, there's 2 atoms in that subscript. So I'm going to write a 2 there. Okay? For oxygen, there's 2 atoms in the subscript there because it is diatomic. It's one of those diatomic elements that we talked about. But on the right, you notice that it's not. There's just 1. Okay? And if you are wondering, well, you just said it was diatomic, so why are there not 2 mandatory over there? Mercury was that way. Mercury ion was that way, right? Mercury 1 always had to have 2 of them. So what's up with this? These are diatomic elements. So they're only diatomic when they are in their element form. That is, when they're alone. If they're in a compound, like you can see oxygen with lithium oxide, right? It's combined with something else. So it doesn't need then to have 2. It only needs to be 2 if it's just oxygen, just pure oxygen, or also pure hydrogen. There's quite a few, and we'll talk about them later. Not that important just yet, but we will get to those. Okay? So right now we got, on the right side for the lithium, you can see I got 2, and then only 1 in that compound, because again, it's not diatomic in the compound. So how do we fix this? Well, the only thing we can do is add, right? We can only add coefficients. So what I'm going to do is in front of that lithium, I'm going to put a 2, right? And that's going to change that 1 into a 2. And then what I'm going to do is look on the right. Now, here's kind of the funny thing, and this is the reality of when you do most of these. Here's what ends up happening, is that you're going to change it. So I'm going to say, hey, I have 2 on the left and only 1 on the right, so I'm going to add a 2. Well, that 2 is going to distribute. So you fix your oxygens, right? But what else did you do? Okay, my oxygens look good, but I also messed with something else, right? Didn't I? I also changed the number of lithiums. So if you look on the lithiums, 2, there's a coefficient 2 there, times another 2. So I end up with 4 lithiums on the right side. Okay, so Now I need to go back. And that's why I said that first example is a little unique in that you just kind of fix two things and you're done. Typically, there's sort of this seesaw effect where you go back and forth and you just sort of tweak it until everything ends up working out. And as long as you don't make too big of a jump, that usually works. So what am I going to do now? Well, okay, now I have 4 lithiums and only 2 on the right. Well, that lithium, I can simply change to a 4. So that's going to get rid of my 2, and now I have 4. So go ahead and look at that reaction real quick before you move on and count them. You have 4 lithiums on the left and then 4 lithiums on the right because it's 2 times Li2. You have 2 oxygens on the left and then you have 2 oxygens on the right because it's 2 times 1. So you are balanced. You have adhered to the law of conservation of mass and made Antoine Lavoisier very happy. All right, let's look at the last example here. And in this one, we're going to get some polyatomic ions. So take a minute right now. I'm going to pause it. Take a minute and go ahead and set up all of the different species. So what I want you to do is write down across the middle every individual element, and if you have a polyatomic that shows up on both sides, you can actually treat that as one thing. So let me show you an example here. Okay, so if you're looking at sulfate, okay, I'm just going to circle this guy here. Okay, now if sulfate is on the other side, if it's anywhere over here, okay, and there it is, you don't have to treat it as sulfur and oxygen. You can actually just treat it as, and it'll pop up on the animation here, but you can treat it as sulfate. Okay? Same thing with phosphate. So find phosphate. Okay, phosphate here, phosphate here. So the cool thing is, you don't need to actually write down, because it would be, of course, very easy just to write down. You could write, you could write iron. Okay, you can write down sulfur, oxygen, sodium, and phosphorus, right? And yeah, it would get pretty complex, because you can see, look at oxygen shows up in a multitude, right? You got 12 here, 4 here, so you got already, you got 16 on the left side. So you got a bunch that you have to consider. The nice thing is you don't need to do that. You can keep your polyatomic ions together. So let's do it, right? So the first thing we have on the left is iron, right? I have how many irons? Well, we'll get to the count later. Let's look at sulfate. Okay. Again, I don't need to separate into sulfur and oxygen if they show up on both sides, and I already showed you that they do. So you have sulfate. I have sodium. Okay, and there's your helpful tip, which I already mentioned. Don't separate your polyatomics. And then I have phosphate. Cool. And there's no other sort of loose phosphoruses or sulfurs outside of those polyatomics, so I'm good there. All right, we'll hit plenty of examples where there are, but for now, not that it's not going to be an issue. So let's look at this, and let's just do our count. So let's count on the left side. How many irons do you have? Look on the irons. You got 2. How many sulfates do you have? Well, remember that little 3 that comes after the parentheses indicates how many of that polyatomic you had. So there are 3 sulfates. And I should be careful to check the other species on the reactant side. In sodium phosphate, there is no sulfate, so I don't need to worry. All right. There are 3 sodiums, and I only have 1 phosphate, because phosphate is PO4. A lot of times students want to put the number 4 down there, but that's not. Phosphate is PO4. If I had more than one of them, I would have written a parentheses around it and then put another number to follow it. All right, so now let's look on the product side, what I end up making. If I look at the irons and everything, I only see 1 iron on that side. Okay, sulfate, I see 1. Sodium, there's 2, it's Na2. And then phosphate, again, I just have 1. All right, so let's get to balancing. Typically what I like to do is, if you can, if there's anything that is alone, and there isn't here, everything's in the compound. This is actually called a double Rothsman reaction. But I would end up saving that towards the end. Same thing if I saw O2, oxygen, I would also save that towards the end. But that's not the case. So let's just start tweaking stuff. The first thing I'm going to do is fix the iron, right? So I'll put a 2 right there, and that will cancel the 1 out. And now I have 2 irons on both sides. Cool. All right, things are looking good. Now that's also going to change my phosphates, right? Because that 2, that coefficient applies to the whole compound there, and phosphate is a part of that compound. So whereas I had 1 phosphate, now I got 2. So I know it's going to, maybe I'm going to have to change something later. But it might work out on its own. You just never know. All right, so go in order. Iron's good. Let's keep working down our list. Sulfate. I had 3 sulfates on the left. I had 1 on the right. So again, sort of the idea here, I'm going to just tweak. I'm going to add a 3 to the right side. And now that gives me 3 and 3. Of course, that also changed my sodium, didn't it? I went from 2 sodiums, now it's 3 times 2. So I'm up to 6. Right. Well, let's go, since it's our next one, let's go change it. So I'm going to put a 2 there, okay, and that should give me, I'm going to multiply everything by 2, and that will give me 6 sodiums. Oops, sorry, that came out a little funky. Cool. Now here's the nice thing, and this is usually a good sign that you're doing something right, is if it ends up working out, by the time you get to the end, things have sort of just worked themselves out. Look at what I had. I had 2 phosphates that I changed in that first part when I messed with iron. Now I have 2 phosphates on the left, and it's already sort of taken care of. I don't need to add anything. I don't need to write anything. I just went back. When I changed the sodium, I also changed the phosphate. And coincidentally, it changed it to the correct number of phosphates. So things are looking good. So I want to just real quick go back, double check, make sure everything's correct. 2 irons, 2 irons, 3 sulfates, 3 sulfates, 6 sodiums, 6 sodiums, 2 phosphates, 2 phosphates. And again, it is 100% balanced. And so I have done my job in conserving all of the mass. All right? And that's it. It takes a little practice. It's kind of fun. Some of them can get really tricky. There's another technique called the algebraic technique that you can use. Sometimes the coefficients can be in the hundreds and the thousands. We've done some extra credit there. But for the most part, it can be done in your head. So we'll try a few more tomorrow. But for now, just focus on this and work on the homework. Most of the examples are really straightforward. And give it your best. All right.